Welcome to the first of two videos about functions, vocabulary, and concepts. In this video, Functions 101, there's a certain mindset that will help you learn the most from this video. First of all, this video is designed to give you a broad sense of what functions are and to familiarize you with function vocabulary and concepts. All the discussions and examples are idea-based, and this is not a how-to video. Please listen with the mindset that you're not being showed math procedures. You might have thoughts while listening like, where is he going with this? What steps do I follow? How do I start the problems? If you start to feel this way, remind yourself that this is not that kind of video. Just absorb the ideas. You may need to watch more than once. Let the journey of functions begin. I'd like to start by taking a guess at what you might think a function is. Have you ever been shown a function like this and asked a question like find f of 10? By the way, if you don't know how to do this, you're the perfect candidate for this video, because this is not something I've taught you yet. But maybe for those of you who do know this, you know to plug 10 into the function and work out the math, and the answer is 32. And while there's technically nothing wrong with any of this, this is completely valid mathematics, this is the perception that most people have of functions. And functions are so much more than this. The purpose of this video is to give you a much broader sense of what a function actually is, beyond what you may have been taught. Let's start with the definition of a function, some basic vocabulary and notation. Let's start with the actual definition of what a function is. A function is a collection of pairs, x, y, where no two different ordered pairs have the same x value. When you first hear this definition, it doesn't make any sense to most people. It's strange how mathematicians have defined a function. In this video, you'll see enough examples of functions where this definition will make sense. But let's focus on one phrase, collection of pairs. Here's an example of a function. You'll notice I have pairs of numbers, and that I've given this function a name. I've decided to call it m for no particular reason. All functions have a name, usually one letter long. But these four pairs, the collection of all of them as one entity, that is the function. The first item in the pair is often called the input, or just x. It used to be called the abscissa, but I haven't heard that terminology in decades. So we'll call the first number in the pair the input. The second one is called the output, or the y value. It used to be called the ordinate. So there's our output. And there's several different kinds of notation we can use to talk about these pairs. And you might wonder, well, if this function has four pairs in it, then there they are. What is there to talk about? Well, there's a lot of notation that has developed over the centuries that you have to familiarize yourself with. So watch this. All of these mean the same thing. Notice that the function m contains the pair 7, 2. Well, that's obvious. It's sitting right there in the function as one of the pairs. There's no mystery to that. Another way to say that is that an input of 7 leads to an output of 2. That means exactly the same thing, and sometimes we use sentences like that. We could also say when x is 7, y is 2. A more simple way of really just making the same statement. Another way to say it is m of 7 equals 2. Notice the m next to the parentheses with the 7 in it. Ordinarily in mathematics, two things next to each other when one of them is in parentheses means multiplication. This does not mean multiplication. M of 7 equals 2 is just another way of saying that the function contains the point 7, 2. We also say 7 maps to 2, or m maps 7 onto 2, and we use this little arrow as a mapping. The concept here behind functions is, yes, they are a collection of pairs, but we tend to think of them as, in some sense, an input and an output, or even a cause and an effect in some cases. And so this last line should be thought of as when 7 goes into the function, 2 as an output is the result. Let's now go through 6 basic ideas that I would like you to know about functions. Once again, here's our definition of a function. Idea number 1. Functions can be finite or infinite. Here's a function m that we just saw in the previous example. Here's a function q. Notice the phrase etc. at the bottom. M is a finite function. It only has 4 points. Finite meaning not infinite. By contrast, q is an infinite function. Notice, for example, wouldn't the function q contain the point 57, 570? That seems to be implied by the etc., meaning that the pattern continues. And this example should convince you that there are an infinite number of pairs in the function q. Idea number 2. Functions can be displayed graphically. I'll show you a couple of examples. First, here's a function that I've decided to call j for no particular reason. And notice that it has 5 points on this graph. Well, if a function is a collection of pairs, but each point on a graph is a x and y pair, then this is essentially just another way to represent a function. By the way, it's the same as if I listed out the ordered pairs that were on this graph. Just a couple of observations about j. First of all, notice that j of 2 equals 4. That's another restatement of the fact that j contains the point 2, 4. They're exactly the same statement. Notice that j of pi is 1. You may recall pi is approximately 3.14, and you may even be able to identify the point whose x-coordinate is pi. And it's also worth noting that function values can be undefined. Let me explain what I mean by that. j of 5 is undefined or does not exist because there is no point contained in this function whose input coordinate is 5. In other words, there's no point on this graph that has an x-coordinate of 5. Therefore, j of 5, which would ordinarily mean the y value when x is 5, doesn't exist because there is no point where x is 5. Here's another function displayed graphically. I've decided to call it z. The first thing worth noting is that z has an infinite number of points here. Now, you may not see any, quote, points on z at all, but consider the following. Z of 2 is 4. How do I know that? Z contains the point 2, 4. Now, something worth noting here is that these big visible round dots don't have to be there for the function to contain that point. This function is being expressed as a line, and that line passed through 2, 4. Whether you see a big obvious dot there or not, it still contains that point. Notice also that z of 5 is 10. Well, why is that? Well, because when x is 5, y is 10 in this function. But does this line contain that point? It absolutely does. Notice the arrow on the end of the line. If we were to extend this line, which is what the arrow implies, a forever extension, then we'll notice here, by extending the axis, that when we have an x-coordinate of 5, we have an output or y-coordinate of 10. You can tell that by the fact that the slope of this line is 2. It's clearly going up 2 spaces in the y direction every time x increases by 1. But you can infer from this that not only is z of 510, but for example z of 300 would be 600. You can't see that point in the picture, but this function contains the point 300, 600. In fact, it would be fair to say in general that this function contains z of any number whose value is found by just multiplying that number by 2. Idea number 3. Functions can be displayed algebraically. Let's take the function z that we just finished looking at and analyze it a little further. Z contains 2, 4, we saw that previously. It also contains 5, 10, but wouldn't it also contain 0, 0? And here's a seemingly random pair, 2.3, 4.6. I got that by picking a random number 2.3 and doubling it. It also contains negative 4, negative 8. You can't see that on the graph, but it would pass through that point. And it contains pi 2 pi, for example, because the y value is twice the x, and so on. Notice that z contains an infinite number of points. There's no way to list them all, and so we use algebra symbols to represent the infinite number of points. In the previous slide, we discussed that you could describe this as z of any number is double that number, or that the y value is twice the x value. But we don't typically like to use any, the word any, in our formulas. So instead we would say z of x equals 2 times x. It's worth pointing out again that this x in parentheses is by no means a multiplication. This is read z of x, meaning the function z applied to the input of x gives the value of twice that value of x as its y or output value. The multiplication sign we don't typically use in algebra, so I'll take that out, and this function would be valid where x is any real number. Just to say a little bit more about this, when we're using algebra notation, we typically use x as our input variable. We don't have to, we could have put any letter there, but the tradition is to have x be your input value, and whatever the formula is doing to that, in this case doubling it, as our output value. By the way, this could also be written in the following notation, which could be read, the function z maps x onto 2x. It looks different, but it would mean exactly the same thing. Idea number 4. Functions can be created without algebra at all. Here's an example of a function that wouldn't involve algebra. Before we show you the function, this is a calendar that represents meetings that a person attended in the month of July. You can see the meeting times in red, shown here. We're going to let the function m be the total number of meetings that this person attended from the first through the end of day D of July. Now, that doesn't sound like the way most people speak. This is sort of a mathematical way of defining a function. And to help you understand the function better, let me try to breathe some life into this using plain English. Before I do, though, I want to focus on the word let. Let is one of the most important words in mathematics. It is a clue to you, the reader, that the person writing the sentence is defining something that before this moment didn't exist. It's basically a definition word. So whenever you see the word let, your brain should send you a message. This person is about to give me a definition of something, and then read it in that context. Okay, so now what does this function actually mean? Well, to understand that, let's ask the question, how many meetings had they attended between the first and the end of the day of the 5th? Well, looking at their calendar, they attended 4 meetings between the 1st and the end of the day on the 5th. So we would mathematically say that m of 5 equals 4. That's just another way of saying this function contains the pair 5, 4. That's just another way of saying that by the end of the 5th, they had attended 4 meetings. Now let's read the definition again right under the calendar. We're going to let the function m of d be the total number of meetings that this person attended between the 1st and the end of the day d of July. And so I hope that definition makes a little bit more sense in reading it. If not, I'll give some more examples. It turns out for this person's calendar that m of 1 is 0. What does that mean? That means by the 1st day of the month, they had attended 0 meetings. M of 8 is 7. What does that mean in this context? By the end of July 8th, this person had attended 7 meetings. Go ahead and look at the calendar and see if you can find the 7 meetings that they had attended by the 8th. By the way, it's worth noting that m of 9 is also 7, because by the end of the day on the 9th, they had still only attended 7 meetings. Notice also that m of 31 equals 20. That represents that by the 31st of July, they had attended 20 meetings. And if you look at the calendar, you'll see there are in fact 20 meetings. It's also worth noting that m of 37 is undefined. Why? Because there's no such thing as the 37th of July. Likewise, m of 13.2 is undefined. Same reasoning. The 13.2 day of July doesn't really make much sense. So that's also undefined. Idea number 5. Functions don't need to involve numbers at all. Here's an example. I'll pause while you read this. This is mathematical speak for a pretty simple idea. I'll give you an example. My mom's name is Barbara. So this function, we could say, includes Franz Rasiedlo, Barbara Rasiedlo. In other words, me, comma, my mother. But it also includes my sister, comma, Barbara Rasiedlo, since, of course, she's also the mother of my sister. And it also includes Barbara Rasiedlo, comma, my grandmother Eleanor, which is her mother. Pretty basic concept. This function illustrates that functions are pairs of things and don't actually have to have numbers whatsoever. It's worth noting that P1 is a finite function because it only has billions of ordered pairs, not an infinite number. Idea number 6. Not all collections of ordered pairs are functions. But wait, didn't I say earlier that a function is a collection of ordered pairs? Yes, that's true. A function is a collection of ordered pairs, but there are also collections of ordered pairs that are not functions. And that's what we're going to see here with 2 different examples. Here's the first one. Consider the set of all ordered pairs password username for a particular public website. Let's call this collection K for no particular reason. And suppose in this public website with potentially millions of users, suppose there are 2 of them that both chose I love money 1000 as their password for the website. Well, since our collection of ordered pairs is password comma username, then this collection K would contain both I love money 1000 Jonathan 2003 for that user, but it would also contain I love money 1000 Sarah Peterson. And why would this cause the collection K not to be a function? Well, look at the definition of a function. Not all collections of ordered pairs are functions, only those for which no 2 different ordered pairs have the same x value. But look at the bottom of your screen here. Here are specifically two ordered pairs that do have the same x value. And therefore, this collection of ordered pairs is not a function. Now, this problem looked at password first and username second. What if we were to consider a different collection, I won't name it, but something other than k, or the same data as k, where the username and the password were switched? Suppose the username were the x-coordinate. This turns out that it would be a function if we considered this collection. We could call this function validateUser. Now, most functions in math are a single letter. So far we've used m, q, j, z, m, and p1. But the name of a function doesn't have to be a single letter. It could be 11 letters long like this one. In fact, in computer programming, the functions tend to have very long and descriptive names to help the programmers understand the functions they're using. But let's look at this in a more mathematical sense. I have a question for you to ponder. Don't you hate it when a website says that a particular username is unavailable? I don't have that problem often with the last name of Rosidlo, but more common usernames are often taken before you can get to them. Now, this seems like a strange question to ask you during a math video, but it's pertinent to this particular function, validateUser. A website won't allow two usernames to be the same. It wouldn't function under those circumstances. So if we consider all the ordered pairs username comma password, if username is in the x-coordinate, then the fact that no two usernames are the same, in other words, the fact that there are no pairs with the same x-coordinate, would make validateUser a legitimate function. And just to go a little bit further, computer programmers use code all the time. I won't show you any specific code here, but there are lots of if-then statements in computer programming. For example, if in this particular context, if validateUser applied to your username equals your password, then of course you'll be granted access to the website. This example shows that functions transcend mathematics and play a very important role in the world of computer science. Let's look at our second example of idea number 6, that not all collections of ordered pairs are functions. Consider the following set. Imagine all the pairs of numbers x, y, for which the x-coordinate equals y squared, or the y-coordinate squared. Let's call this collection of pairs T, for no particular reason. Just to get a sense of what T looks like, let's pick some random examples from this collection of pairs. If my y-coordinate were 3, looking at the equation near the top right of your screen, if y were 3, x would have to be 3 squared, or 9. Convince yourself that this ordered pair is a member of the collection T. It essentially is, because 3 squared equals 9, or more generally, y squared equals x. If we wanted there to be a point whose y-coordinate was -5, the x-coordinate would have to be +25, because -5 squared is 25. You get the pattern, hopefully. T also contains 0, 0, because 0 squared is 0. It also contains radical 7, 7, because if you square radical 7, you get 7. If you're watching this video with no knowledge of radicals, don't worry, that's not where we're going with this example. And T also contains -3 as a y-coordinate and 9 as an x-coordinate, because -3 squared is 9. Now T contains an infinite number of pairs. This is just a quick showing of 5 of them. But there's something worth noting here. There's something about these two in particular that you see highlighted that shows us that T, the collection T, is not a function. Look at the definition at the top. This is a direct violation of the definition. No two different ordered pairs may have the same x value, but these two different ordered pairs have the same x value, and for that reason, t is not a function. Let's just go down another road here where we examine what would happen if we were allowed t to be a function. We're not going to, it isn't a function, but I want to give you a sense of why they chose the definition for function that they did. If we were to allow a situation like this to be a function, 9 would map to 3, but 9 would also map to -3, you'll notice by looking at the two highlighted ordered pairs. But the very concept of a function is that inputs map to a specific output, not that an input can map to two different outputs. That concept that each input should map to a single output is violated here, and that is why they wrote the definition the way they did, to make things like this not be a function. By contrast, it is okay to have two different inputs that map to the same output. For example, take the mother function that we examined earlier. In that function, we saw that it contained these two ordered pairs. Restated, both me and my sister map onto our mother, and that's the way this mother function was written. For that reason, you can see that two different inputs map onto the same output. This is fine, and despite this duplication, P1 is still a function. In other words, it's okay for two different inputs to map to the same output. It is not okay for two different outputs to map to the same input. Of course, this raises an interesting question. What do we call a collection of ordered pairs if it fails to meet the definition of a function? In other words, what do we call t here? We can't call it a function. Well, there's no actual name for it, but here's a word worth knowing. Collections of pairs, whether they're functions or not, are called relations. If you just wrote down a random bunch of pairs of things, that is by definition a relation. Now, before we proceed, I'm going to pause. Please read idea number 6 near the top of your screen to yourself. In light of that, here's a restatement of idea number 6. Some relations are functions, while other relations are not. In other words, a relation is a collection of ordered pairs. Sometimes that turns out to be a function, and sometimes when there are duplicate x values, it's not a function. But that still leaves the question, what do we call this x equals y squared collection of points? Well, what's the word for a collection of pairs which is not a function? Unfortunately, nobody ever made up a word for that, so we just call it a relation which is not a function. Now that we've covered the 6 basic ideas that I needed you to know about functions, let's go on to some more vocabulary. We're going to be looking at domain and range, one-to-one functions, and inverse functions for the remainder of this video. First, let's talk about domain and range. When we talk about the domain of a function, we're saying that it's the collection of all input values or x values. Similarly, the range of a function is the collection of all outputs or y values. Let's look at an example. Here's function q that we've seen earlier in this video. The domain, being all of the inputs or x values, is 1, 2, 3, 4, 5, 6, 7, and so on. Now, we could express the domain this way. There's another way we could express it with braces around it. Braces in mathematics are generally used for a collection of things. Regardless of whether we put the braces there or not, we're still talking about the numbers 1, 2, 3, 4, 5, 6, and so on, but braces make it a little bit more formal. These, by the way, are called the natural numbers and are denoted by a double-scripted n as shown here. Any one of these four answers is a valid response to the question of what's the domain of the function q. They all represent the same thing in slightly different ways. The range, being all of the output values, is obviously all the y values, 10, 20, 30, 40, 50, 60, and so on. To be more formal, we could put these in braces. Let me show you a couple of even more mathematically formal or more proper ways of expressing the range. Notice that all the numbers in this set can be represented as 10 times 1, 10 times 2, 10 times 3, 10 times 4, and so on. Or more generally, 10 times k, where k is any natural number, 1, 2, 3, etc. It's not required that you express the range this way. The two lines above it are satisfactory ways of describing the range, but this looks a little better, a little bit more formal. Here's another way to do it, which is essentially the same thing. This line here is a mathematical symbol that takes the place of the words where or such that. So this is saying all numbers 10 times k, where k is 1, 2, 3, and so on. I could also express it this way, where this symbol represents belongs to or is an element of. All of these ways of expressing the range represent the exact same set of numbers in different ways. The degree to which your math professor may want more formalized answers versus less formal ones towards the top, of course, is up to them, but suffice it to say that all of these represent the same thing. The beginning brace in a construct like this is always pronounced the set of all when we're going to describe the set of all objects that match a certain condition. So, for example, just for pronunciation purposes, this would be pronounced the set of all 10 times k, where k is any natural number. Let's take a look at another example of domain and range. Here's a function j, which we've seen earlier in this video. Remember that j has 5 points, and here they are. The domain of j, meaning all of the x values, are these numbers here, which look better when they're in braces to show that they're a set or collection of objects. The range is all of the y values or outputs for these 5 points, which, as you can see by looking at the points, are these numbers. It wouldn't be uncommon for me, as a professor, to see a student write this thing as range. Look at the bottom right corner of the screen, and while it's technically a correct answer, it dramatically misses the point of what the range is. Students who write this 02441 have the mistaken impression that the range is a list of y values in the order in which they appear. But the range is really just the set of all numbers that appear as y values. And so while this last thing is technically correct, it really misses the mark on what range is, and I wouldn't recommend writing it that way. Let's look at another example of domain and range. Recall the function z from earlier in this video, where z of any input is 2 times that input for any real input x. The domain of this function is all possible inputs. That's the definition of domain of any function. But notice for function z, any number can be an input to this function, because any number can be multiplied by 2. And if any number can be an input, and the domain is all possible inputs, then it's fair to say that the domain is all numbers or all real numbers. By the way, this double scripted R is a symbol for all real numbers, so it's acceptable to put that as well. It means the same thing. Sometimes you'll also see the set of real numbers listed as the interval from negative infinity to infinity. If you're not familiar with interval notation, it's not the main point of this video, and I wouldn't worry about that now. As far as the range goes, the range, of course, means all possible outputs for this function. Well, it turns out that any number can be an output to this function. And just to give one example of that, consider the following. Suppose we wanted this function to have an output of 50.6. That's just a random number that I made up to prove a point. So the question then becomes, does anything map onto 50.6? Because if it does, then 50.6 is part of the range. But you can answer what maps onto 50.6 by just dividing that number by 2, which gives us half of that, or 25.3. Since z is the doubling function, z of 25.3 is 50.6. Now again, there's nothing special about 50.6. It's just a random number I made up, but it illustrates that, or at least the concept of finding what maps onto it, illustrates that whatever real number I pick and ask, is that number in the output? The answer will always be yes, because any number I pick for the output, I can cut half of it, and that number will map onto that output. Therefore, any number can be part of the output, and the range would be all real numbers as well, which can be expressed in these three ways. Let's look at yet another example of domain and range. Recall the function that was related to the person's calendar and the number of meetings that they had attended in July. Remember that D represented the day of the month, and M represented the number of meetings that they had attended from the first through that day. The domain of this function, being all possible inputs, is all whole numbers between 1 and 31, because the inputs are the days of July. We could also write that this way. The range means all possible output values. In other words, all the numbers I would get if I plugged 1 through 31 into this function. So what I did is I did just that. I plugged all the numbers 1 through 31 into the M function. These are the results. In case you forgot the meaning here, watch this one in particular. M of 11 is 8 because between the 1st and the 11th of the month, this person had attended 8 meetings. Just to remind you how this function worked. This list here represents all possible outputs, or the range, and therefore the range is just that list of all possible outputs. And our last example of domain and range can be shown by the mother function that we analyzed earlier in this video. You may recall that the inputs of these functions are people, and the output of this function are that person's mother. Therefore, the domain is all people, and the range of this function, meaning all possible outputs, is all moms. I'd like to now switch gears to a concept called a one-to-one function. A one-to-one function is a special kind of function. Here's the definition. I'll pause while you read. You may notice that this definition sounds almost like the definition of a function itself. Both of them have the requirement that there never be a repeated x value. But for a function to be one-to-one, then we require additionally that there's never a repeated y value. I'd like to look at 4 examples of functions that we've seen already in this video and analyze them for whether they match the criteria for being a one-to-one function. The first example, you may recall, was a set of ordered pairs, username, password, for a particular public website, and we called this function validateUser earlier. Suppose that there were two users of this website that had the same password. I'll use the same two examples that I had earlier. If this were the case, that both of these different users had the password ILoveMoney1000, then we would be able to say that this function is not a one-to-one function. The logic being, there are two different input values, Jonathan 2003 and Sarah Peterson, both of which have the same or map to the same output value, ILoveMoney1000. And if you look up at the top of your screen for the definition of a one-to-one function, it's a collection of pairs where no two pairs ever have the same x or y value. But if, in fact, two people have the same password, then that represents two different pairs in this function that have the same y value. And since that can't happen in a one-to-one function, this function is not one-to-one. Here's another way to think about one-to-one functions. A good way to think about it is this. A function is one-to-one if the following is true. For any given output, we can uniquely determine the input from which it came. Or stated another way, can we work backwards from output to input? So if I said to you, there's a username password combination that maps onto or has a password of ILoveMoney1000, which username did it come from? Because there are at least two people who have that password, we wouldn't be able to uniquely determine the input or work backwards from a given output. And that is what makes the validateUser function not being a one-to-one function. Let's look at another example of a function and determine whether or not it's one-to-one. Here's the function q that we saw earlier in this video. If we know the output, can we uniquely determine the input or work backwards from that output? This is the question that ultimately will answer whether or not q is a one-to-one function. To consider this further, let's ponder the following example. Suppose we knew that the output for some particular input was 840. Well, what number would map onto 840 using the function q? Well, clearly 84 would map onto 840. But there's nothing special about the number 840. In other words, whatever number in the output I would have picked here, there would have been only one single thing that could have mapped onto that. In that sense, given an output of this function, we can uniquely work backwards and determine what input it came from. And this one example should convince us that any output can be mapped onto by only a single input. Another completely different but equivalent way to state this is that there are no repeated y values in the function q. Regardless of which way you look at it, the final conclusion here, q is in fact a one-to-one function. Here's another function we can analyze to determine whether or not it is a one-to-one function. Recall the function where m is the number of meetings that had been attended between the 1st and the 10th day of July. To answer whether this function is one-to-one, we need to ponder whether or not, for any given output, if we can uniquely determine or work backwards to the input. Well, you may recall that we already looked at all 31 outputs to this function. And For example, if we were to ask the question, through the m function, what maps onto 9? Looking at the list of function values, it's clear that 3 different things map onto 9. By the way, this is really just a reflection of, as of the 13th, 14th, or 15th of the month, regardless of which day you were to choose, this person had attended 9 meetings. But the fact that 3 different things map onto 9 precludes m from being a one-to-one function. Let's look at our final example of functions to determine one-to-oneness. Consider the function z we've seen earlier, where the input doubled equals the output. The question to determine whether z is one-to-one is equivalent to saying, if we have any given output or we know the output, can we always uniquely work backwards and determine a single input? Well, to ponder that, let's consider a specific example. Through the function z, what maps on to 81? Well, it turns out 40.5 maps onto 81 because 40.5 times 2 is 81. Well, what else maps onto 81? Well, it should be easy to convince ourselves that 40.5 is the only number that you can double and get 81. So only one thing maps to 81, but 81 isn't special in any way. This one single example should convince us that any output can only be mapped onto by a single input value. Therefore, m is, in fact, a one-to-one function. I'd like to change gears to one of our final vocabulary topics of the day, inverse functions. Here's the definition of an inverse function. Plainly said, if a function is a list of ordered pairs and we reverse all those ordered pairs, we then have the inverse of that function. Here's an example. Consider this function g. It's not something we've seen yet in this video, but it's clearly a simple function consisting of only 4 points. If I were to take those pairs or points and reverse the x and y coordinates, notice I've done that here, then this new list of ordered pairs, this new function, which could be displayed graphically or as a list, is called the inverse of g. A quick note about the notation, the g with the -1 hovering over it. It's pronounced g inverse. Do not call it g minus 1, and don't even think of the -1 as an exponent. It's not. It's simply a -1 hovering over above the g as a representation of reversal of x and y coordinates. So that's a pretty simple concept. The inverse of a function is the reversal of all the pairs. No big deal. I'd like to add on to this concept by showing you something interesting when we look at the graph of a function and the graph of its inverse. And to see this relationship, I would like to superimpose all the points from the g graph and the g inverse graph on the same set of axes. Now this may look like some random scattering of points to the untrained eye, but it turns out that there is a unique relationship between the points of g and the points of g inverse. Let me give you that visual and physical relationship right now. It turns out all the points of g are mirror images through this line, a 45-degree line through the origin. This line is called the line y equals x. It's a fitting name because every point on it has equal y and x coordinates. This line passes through 1, 1, 2, 2, 3, 3, and all points for which the y equals the x. But putting the name of this line aside, it's a very special line to compare functions and their inverses in a graphical sense, because it turns out that every point in G is the mirror image through this line of some point on G inverse, and vice versa. For example, these 2 points are mirror images through the line. These 2 points are mirror images through the line, as are these 2, and as are these 2. In general, it's fair to say that if you represent a function and its inverse graphically, those 2 functions will be reflections of each other through the line y equals x. Let's look at another example of an inverse function. Consider the function z, the doubling function, that we've seen several times throughout this video. To get a clearer image of what the inverse of z might mean, here's a different way to think about an inverse function. Yes, it is a reversal of pairs, but it has a different purpose that sheds a little bit of light on why it was created and what the actual intuition is behind an inverse function. If I were to ask, what is the value of z inverse of 12? That would be the same as asking, in the original function z, what maps onto 12? Well, clearly in the original doubling function z, 6 maps onto 12. Equivalently, looking at the right side of your screen, z inverse of 12, meaning working backwards from 12, works out to be 6. That completes all the examples and concepts about functions that I wanted to convey during this video. I'd like to end by giving you a certain mindset that I think will help you as you work on function problems throughout your textbook or website or wherever else it is that you're doing mathematical problems related to functions. So while this video showed many examples of functions, they were not presented in a way that provides you a procedure for what to do when presented with function questions in future assignments. Again, recall, this was not a how-to video. Still, everything you need to know about functions was presented in this video. Now, most students, once they get to the point of actually having to answer questions about functions, have this moment of panic because the function problems require 2 things to be solved. One, a full understanding of the ideas of functions, and second, a willingness to let your mind kind of wander and explore how any particular function operates. And this is a particularly uncomfortable environment for many students. Students, and rightfully so, are more comfortable when there's a collection of procedures that they can follow and guide them to a solution. Fortunately or unfortunately, depending on your perspective, functions do not fit this category. So what can you do about it? Well, first of all, when you are encountering a stressful situation because you're solving a function problem and there's no particular procedure or outline of how to go about it, tell yourself to relax and recognize that there is no such procedure and that you shouldn't be looking for it. A second thing that you can do is, for any given function, you can try to find several pairs that the function contains. I do this even when I'm not asked to, because the more random points that you can find on a function, the more likely you are to understand the function, and in turn, the more likely you are to be able to answer the question at hand. So when I'm given a question about any particular function, I will find several points that it contains, again, even without being directed to do so. Because once you do that, you have a better feel for how that function operates. And once you have that, you can answer other questions about it as directed. So the mental state of mind required to answer questions about functions is one of a willingness to think creatively, without a given set of directions. And contrary to most other things we do in math classes, this is real mathematics. So, enjoy. And that completes the first of our 2 videos in this series.